Okay, now that I got this base well underway, it's time to start taking apart the coil here. When I built this coil in the first place in 2011, I used a program called javaTC. You can find that online. I'll provide the link for you right here. And you can go to it, navigate to it, and you can see that it's going to require a set of inputs that are essentially the geometry of the coil you're trying to build, the capacitances that you've set up, and things about the power supply that you'd use. Now, javaTC, as Bart currently has it arranged, is set up to give you power calculations if you're going to do a spark gap coil. This coil actually started out as a spark gap coil, and over the years, singular, I actually converted it to a dual resonant solid state coil. It turns out that the equations for the resonance of the top hat and the secondary and the primary are the same irrespective of what type of power supply you use. So in this video we'll go over to javaTC and we'll run the parameters for the geometry of the secondary and the top load, as well as the primary, just to re-verify exactly what the resonant points were and the tuning points. Now the thing is that I had done this years ago, but I didn't save the output, so I don't remember exactly what those tuning points and parameters were. However, I do have the coil in front of me, and I know that it works, so I can reverse engineer it. The process that, and in fact, maybe one of the things we can do is you could use this as an example coil in javaTC, so that you could yourself enter the parameters for whatever you're trying to build. Now, this is a rather large coil. This secondary is about 8 3/4 inches in diameter. It's about 36 inches in height. I've got a professionally made top load here that came from a company. I'll also go look that up and provide you the link. Came from a company on the East Coast that does custom spinning. So this was not an inexpensive item. I had it custom made. You could find these things online, but they're very rare. So I had this one made myself. This is a 2-foot by 6-inch minor diameter. 2-foot major diameters. This is the major diameter, this is the minor diameter, so it's 24 by 6. Had that custom made, everything else I made myself. So what I'll do is, I don't remember precisely what the parameters were that I originally entered when I built this thing, but I'm going to reverse engineer. I'm going to take some measurements, I'll show you, I'll start breaking this down, I'll show you what's in there, then we'll go over to javaTC, we'll enter in all the measurements, and we'll see if I can actually get the tuning points back that I started with. Alright, well let's start taking this apart. So this is just a piece of brass that I was using as a breakout point. Breakout point means that it provides a place for the arcs to emit from. Basically, if you start doing any kind of electric field theory, you'll find that when you get to a point, the field gets concentrated and very strong at a point. You've got an electric potential that's being built up around this surface, and it will concentrate at the points on the surface. And it's basically, you know, if you just integrate the field over the whole surface, where you have smooth parts of the surface, the field is lower. Where you have very sharp, pointy parts of the surface, like on this piece of brass, the field will be very high. And what will happen is the arcs will tend to emit from those pointy spots. Now, if you don't have one of these, the arcs are going to emit from wherever, you know, kind of in a chaotic manner, wherever it finds a place of the highest possible potential. That could be where, I mean, this thing is pretty dusty. It could be because you got a piece of dust. You notice there's some nicks on this. It could be where there's a nick, or for a spark gap coil, that's not too bad. The breakout point, you know, you don't need a breakout point. It's kind of cool to watch the arcs come out from all over the place on the top. It makes for a good show. For a DR coil, you want to have the sparks regularly breaking out. You don't want it to be a random emission, because you can build up some back current, as it were, and that can really play havoc with your solid-state drivers. So you want the sparks to be emitting regularly. That's why I just used a breakout point. In fact, you could put anything on here. I'm not even sure that it has to be a piece of metal. You know, basically anything reasonably conductive. I just happen to have this piece of brass laying around. You could tape a nail to that. You could, you know, basically anything that creates a point will concentrate the electric field, and the arcs will emit. Now, you need to have a top load. The top load provides the capacitance, and as I mentioned in the first video, what you're looking for here is you've got an inductance that's presented by the secondary, which is the L component, the inductance component, and you've got a capacitance, which is represented by this top load. And the geometry of the top load and of the secondary is what presents those values. It's a purely geometry problem. There's no electronics involved at all. I mean, there's electric fields, but if you're going to solve the equations, it's just algebra and it's geometry. Luckily, the javaTC program handles all that for you. So all you have to do is put some measurements into that program, and it handles figuring out the L and C for you. So you don't have to worry if you don't understand the electronics or the electrical effects. That's all been worked out. So there's the top load, or rather the breakout point. And here's the top load. Let me get a tape measure. Now we're going to be entering all these measurements into javaTC. So I'm going to show you here is that this is roughly, I don't know if you can see that, but it's 24 inches that way, and this way we're talking 6 inches. All right, so it's a 24 by 6 top load. I didn't even really have to measure it because I know what it is. I'm going to lift it off, and as you can see, it's pretty dirty, having not been used for years. And it's a piece of beautifully spun aluminum. But it's also kind of fragile. I mean, if I was to drop this, it would dent, it would scratch, and that's not, you know, generally not good for the let's say the homogeneity of the surface that it's trying to present, and it'll create other breakout points, which we really don't want. We want to control where the arcs come from. So we'd like this to be as smooth as possible. So we take care of this. All right. So what I have up here is a spacer. And this spacer served to raise that toroid a little bit higher. And I'll explain why. When we're doing javaTC, you'll see why that was a good idea. And underneath here, what you see is a copper strip. So that copper strip is simply connected to the to the end of the coil of wire that's around this secondary tube. And it's connected onto this weld nut that I put in. Now there are as many ways to terminate these secondaries as there are people. I chose this way. I think when I rebuild it, I may do something slightly different. But it seemed kind of solid. I actually just soldered it right here, and then it's all gummed up with this EnviroTech stuff and various epoxies. And connects to this weld nut in the middle. Then I had this brass. Brass is a better conductor than slightly better conductor than the steel in the weld nut, and weld nut is just connected to this surface, this surface is cutting board material. This is a piece of it. It's HDPE cutting board material. You can buy it at any cooking store, in fact. Just get a piece of cutting board. Now I got a piece of cutting board, and I created the circle with a router. I actually used my lathe to smooth it out. You don't have to do that if you don't have a lathe. You can just smooth it out by hand, or spin it any way that you can find fit. But essentially, this is just a piece of cutting board from Williams-Sonoma or Sears and Roebuck or Walmart, or Target. And that's what this is. Okay, so I've got a piece of brass, and this is just a brass stud I got from Master Car, and then this here is a weld nut, called a weld nut. So as you can see, the weld nut screws on there. This is not a 1/4 by 20. It might be a 1/2 by 13 or 5/16 by 18, I think maybe. And all I did was I have a weld nut there, I have one here, and this just provided a really nice surface to rest the toroid onto, and that gave me the ability to raise or lower the toroid. And the calculations that you're going to use to create the L's and C's are dependent on how high this toroid is sitting on top here. I had placed that on there and let the toroid sit on there, and that gave me roughly, if you take this measurement, now what I'm going to do is I'm measuring from the last tight turn on the top of the coil here. So as you can see, the secondary wiring runs up to about there, and then there's a blank spot. And so there's about 1 inch. I left 1 inch on the top and the bottom. So this particular core secondary coil ends here 1 inch from the top. Now there is another turn that's just kind of a wild turn that just provides the connection, and I didn't include that in the calculation, but that's so minor it doesn't matter. So there's 1 inch there, and then this provided an extra 1/2 inch. So when I rested the toroid on top of here, that gave me an extra actually it was sitting like this. It gave me an extra 1/2 inch. I really didn't need this plate, except it gave some more mechanical balance to the thing. Okay, now let's get into the secondary itself. So by the way, just to remind you of the measurements, it was a 24 inch by 6 inch minor diameter, major diameter 24 inches by 6 inch minor diameter toroid that was 1.5 inches, placed 1.5 inches above the top turn of the secondary, and you're going to need to know that when you set up javaTC. And then I'm measuring from the top, the last tight turn on the secondary, to the bottom of the toroid. And actually, when I say the bottom of the toroid, you'll notice that the toroid is a donut shape, and there's a plate in the middle, exactly in the middle. So this is the height from the last turn to that plate in the middle. All right? When you set up javaTC, you'll see that you need to know that dimension. This allowed me to raise and lower the toroid. So this secondary is actually what is currently called an 8-inch in diameter piece of, this is an 8-inch piece of PVC ducting. It's meant to be an air duct. I got this from McMaster-Carr as well. It's called an 8-inch in diameter. I can tell you that it is not 8 inches. I can tell you it's not 8 inches in diameter. It's almost 9 inches, actually. Now, it's sold as an 8-inch piece of plenum, but it comes, and mine is about 8 7/8. So the OD on this, the outer diameter, is about 8 7/8. The inner diameter, which really doesn't count for anything in our calculations, is more like it's looking like 8 1/4, 8 3/16 kind of. And probably the people who are actually using this in construction are using it to run air ducting, and so the ID is more important than the OD. For us, we don't care about the inner diameter. We're not using that for anything. We're only using the outer diameter for our calculations. So the outer diameter of this is 8 7/16, roughly. Let me make sure I get that right. Excuse me, 8 7/8. It's about 8 7/8 in diameter. So they're selling 8 7/8 as 8-inch PVC duct. What I've done is, and maybe in the course of these videos I'll make another one of these, but I don't have to, but it's an interesting process. I took the duct. The duct comes, it's made by a company called Harval. The outside is kind of rough. It's not exactly cylindrical. And so I smoothed it out and made a little lathe I put on my bench, and I turned it with a DC motor. And you've seen other people do this at YouTube. And I smoothed it out the best I can. Then I painted it with red Gliptol red, which is the stuff they use for engines, for heat protection for engines. So I painted it with Gliptol red. I don't know if that's necessarily required for any reason. It just makes it look cool. And I know that other people have done it. And there's been some theory that the gray PVC at these voltages can actually be conductive. I've never noticed that at all. But certainly painting it with Gliptol red makes it completely insulative. It actually adds another couple thousandths of an inch, because the paint itself is not infinitely thin, so it adds another couple thousandths of an inch to the outer diameter of the tube. But that doesn't really factor in your calculations at all anyway. So what I did was I painted it with Gliptol red. There's actually 2 coats on there. And then I drilled and tapped at 8 spots around the outside, and with 10 by 32 plastic 10 by 32 screws, or let's say bolts, I drilled into the top here and tapped it in, and that's how I screwed in the cutting board material. And if you were to look around the edge, it's kind of hard to see. Here's a screw, here's a screw. They're all covered in Gliptol red, so as you can see, I've got some screws. They're painted with Gliptol red and also covered with this EnviroTex, which I'll get into in a moment. So then the wire for the secondary is 26 gauge, and the way I remember that, now I didn't remember it was 26 gauge. I had a spool of 26 gauge wire laying around. That's why I'm pretty much assured of it. But there's about 2,000 turns along the entire length of this. So I measured, actually what I did was I went back and remeasured how many turns per inch. Actually what I did was I used this thing, used this little ruler. I took a picture with my iPhone in black and white, and I zoomed in on it, and I reverse engineered that I had about 58 turns per inch, and 58 turns times 35 3/4 get me around 2,000 and change turns. This is the magnet wire I used. Got this on eBay. This is a brand new reel. I was planning on making another secondary at some point, never did. So as you can see, it's relatively thin. I think it's about 100 thousandths. 100 thousandths, about 10 thousandths, so it's about 1/100th of an inch in diameter, single coated, and you can get this on eBay. They sell these things. They sell them by the pound. When you run javaTC, it'll tell you how many feet you need, basically. So you can pretty much take that to the bank. Now, why did I pick 26 gauge wire? Because I knew I needed to get about 2,000 turns to get the frequency that I wanted to keep the resonant frequency low enough for the transistors that I was using. The resonant frequency of this coil turns out to be in the 60 kilohertz range, which is maybe even a little too high, but it's about what you need for a transistor-based Tesla coil. For a spark gap Tesla coil, you can use whatever you want. Now, one rule of thumb: if you use thicker wire, like 18 gauge wire, I've used that on some of my older coils. It's generally speaking, the thicker the wire, the higher the resonant frequency is going to be. A high resonant frequency is not necessarily a great thing, but for a spark gap coil, it doesn't matter. For a transistor-based coil, it's very important that the resonant frequency be within the sweet spot of the transistors that you're using. Otherwise, things may blow up or not work. Generally, things won't work. So 30, 40 kilohertz is kind of where you want to be for these CM300 based coils. This one is 60, and I'm using CM300s, and it seems to work just fine, but I don't run it at super high power. So and don't worry if you don't understand everything I just said. We will run javaTC, and the thing to keep in your head right now is thinner wire, more turns means a lower resonant frequency. Lower resonant frequency is favorable for transistor-based Tesla coils. For spark gap based Tesla coils, it almost doesn't matter. It really does matter at the end of the day, because it'll dictate what type of capacitors and the size of the capacitors you use on your primary circuit. But you don't care if it's 100 kilohertz resonant frequency for a spark gap, whereas you're not going to run a DR coil at 100 kilohertz. Okay, so that's the secondary. Okay, so here's the primary. Again, this stuff is filthy, and I would not even deign to try to run this at the moment, because with all this dust on here, God knows the thing would spark and arc and all over the place. So I really need to take it apart. This is 1/4-inch refrigeration tubing. It's 1/4-inch refrigeration tubing, spirally round in an Archimedes spiral, and I'm using these. This is not G10, but it is I think it's G4 garolite, red garolite. It's temperature resistant to 900 degrees Fahrenheit, which we're never going to get to, so I'm not worried about that. And it's utterly electrically insulated. So, and it's sitting on top of this round piece of acrylic that I got from Tap Plastics, and I was using it for something else. In fact, when I made this coil, I just ginned it up out of parts that were laying around. I wanted to have a sister coil to my big one so that I could play duets on MIDI duets, and so I just really quickly hacked this together with parts I had laying around. So you'll notice there are extra holes in here that don't belong and whatnot. And the critical thing, the measurements that we need to make for javaTC are, let's get the ruler, are what is the radius of the inner turn, the first turn. This is the first turn right here. You can see that it comes out right there. What is the radius between the center point and here of this first turn? And when they say radius, they mean the inside edge of this first piece of coil. And when I measure that, I'm seeing I'm getting about from the outside edge the secondary to here is about 1 3/4. So I know from the outside edge here is 1 3/4. I know that the radius of the secondary itself is about 4 7/16. So I add those two things together, and I get 6 and I can't do it mentally, but 6 and 6.3, 6.4, something like that. Anyway, we'll do that on the javaTC. So that's the first important measurement, is where does this outside edge come in. The next measurement is what's the spacing, what's the thickness and spacing of this coil. So this is 1/4-inch tubing, so by definition it's a 1/4-inch wide, and I put it a 1/4 inch apart. So there's a 1/4-inch gap between each turn. So that means between the center point here and the center point there is a 1/2 inch. So each turn is a 1/2 inch beyond the other one. Now, I don't remember what the tuning parameters were, but I do know this. This coil was working when I stopped using it. And here is the tap for the outside edge of this primary. So electricity comes in from here through the bottom into the first turn, spins around 1, 2, 3, 4 times, and then goes through this tap. This outer core is not being used at all. So here's the tap. So I'm using roughly 1, 2, 3, and almost 4 full turns, right? So almost 4, maybe 3.8 or 3.9 turns or so. So when I run javaTC on this and I put in all my measurements and I ask it to tell me where I should tap this for resonance, if I don't get a number that's close to 3.8 or 3.7 or 3.9, let's say 4, I'll know that I did something wrong, because I know this coil works. So in this setup. Okay, so again, I've measured the diameter here, the radius to this, and was 1 3/4 to the outside edge. Actually got to add another 1/8 to get to the middle, but 1 3/4 to the outside edge plus the diameter, the radius of the secondary itself. That's a measurement we need. We need to know how far away that is from the first turn of the secondary, the first turn being there, which is 1 3/8. Another measurement we need to know is what is the height of all of these turns on the secondary. Now what I'm going to do is measure it from, if we can zoom in here, we can see that the first turn is not all the way at the bottom of the secondary tubing. Now, because of the parallax, you can't really see what that measurement is. But I'm gonna measure it with this. I'm gonna tell you that it's an inch. It doesn't look like an inch because we're looking down on it, but between the first turn here and this bottom point is actually an inch. I have the same on the top. Now, when I measure this secondary, I'm not going to worry about the bottom edge of this of the tubing itself. I just want to know what's the distance between here and the top. And what I'm going to tell you is that the distance is about 36 inches. Almost exactly 36 inches from this bottom edge of the first turn to the last edge there. So that's something that we got to record. And if I zoom out and we can look at the top, you can see very clearly without the parallax is about an inch there. So between this edge and the bottom edge is about 36 inches. That's a parameter we need. So we know the diameter, we know how big the total length of the number of the turns of the secondary. We know the top load dimensions. We know the spacing between the size of the wires in the primary and the spacing between them. Two last things we need to find out is what is the height distance between the bottom. Let me go back down to here. Another critical parameter is what is the height delta between, let's see, the top of this and the first turn here. Okay, so here's the interesting parts of the primary. So here you see the first turn coming up from the power source down here, and here you can see the tap. That's where the current is exiting from. So current is starting here, going around 1, 2, 3. Oops, I should count this in a way you can see. 1, 2, 3. Hard to see because I've got this weird parallax. 4. So almost 4, maybe 4.9 turns. All right. We're gonna keep that in mind, because if I run javaTC and I don't get that number, I know I've done something wrong, because I know this coil works. Now, when you're using javaTC to set up the parameters for a coil that you don't know, it'll tell you where you should tune. And the tuning means where this tap should be along this coil. You'll notice I'm not using this turn at all. This turn is useless. I put it in there when I didn't know exactly how many turns I needed. I actually soldered it on, added it, and it turns out I didn't need it. I could cut this thing off right here. I could actually cut the tubing right here and forget about this whole outer turn, and everything would be fine. Okay, so now the next thing I need to know, and again, that's how this is tuned. It's tuned at 123.9 roughly. If this tap was further out this way, it might be a full 4 turns. But I'm guessing that looks like about 5%, so it's maybe 3.95 of turn. So that's how I'm going to double check my numbers. Now the other thing I want to know is what's the height between where this starts, the height difference between that and the first turn of the secondary. That's going to be a critical factor, because we're going to need to raise or lower the secondary to adjust the K. The K is the coupling factor between the primary and secondary. Remember from the first video that what this Tesla coil is two coupled LC circuits, 2 resonant coupled inductance and capacitance circuits, and they're coupled by magnetism, and the coupling factor is K. And the K is adjusted by raising, well, there's many ways you could adjust K. You could actually move, if this primary were closer to that, it would be a higher coupling. If this primary started further away, it would be a lower coupling. If the coupling is too high, and we've already built the thing, we can adjust it by raising the secondary. Basically, the distance between here and the first turn, or in the turns here, you want it to be further away, and that reduces the coupling. For a Tesla coil, you don't want the coupling to be too high. You actually don't want a lot of the energy, 100% of the energy from the primary to get to the secondary. Even though you think you would, you don't, because it will create problems called racing arcs and other things. The circuits are resonant, so the current and the voltage in the secondary circuit is going to build up at the resonant frequency without you doing too much to it. Again, it's like pushing somebody on a swing. You don't want to push them at 1,000 miles an hour. You just want to keep pushing them slowly, and the oscillations will build up on their own. So the coupling you want to be reasonably low, and javaTC will tell you what the appropriate coupling is. If the coupling's too high, what's going to happen is voltages are going to get excessive along the outside of this secondary, and you're going to create standing waves, and you could actually calculate these things, but what's going to happen is the arcs are going to start coming out of the secondary itself and create burn marks. I don't know if we can see this. You can see, let's take a look here, see if you can, if I can get you into where my finger is. Let's zoom in. So you can see that burn mark there. That's where, before I had this thing tuned correctly, I actually had racing arcs. So arcs were coming out of the secondary and merging in with other points, and that's due to a buildup of standing waves, which are coming greater and greater and greater. And instead of creating a high voltage exclusively at the top load, you're getting high voltage points along the secondary. And that's what happens when the coupling is too high. So you don't want to do that. Let me see if you can get it even closer to one of these burn marks. So the ones I've got now, let's see if it'll focus on that. Focus. It doesn't really want to focus on that. I was lucky. These burn marks didn't destroy the secondary. You can get at a point where the burn marks will actually weld together individual turns on your secondary, or they'll actually cut the secondary, just blow them up, and then your secondary will be disconnected and needs to be repaired. This secondary is coated with javaTC, so it would be very difficult, if not impossible, to repair. Actually, what happened was when I turned the wire onto the coil, I first coated it with spar varnish, 2 coats of spar varnish, and then the javaTC on top of that. The spar varnish serves as a binder, glue, to hold the turns together, and then the javaTC protects the whole thing. Okay, so let's go back to calculating the K, and actually this is not such a bad shot. What I want to do is measure the vertical distance between the top of this coil and here, the bottom there, and I'm about 1 inch. So that kind of coming out. Due to the parallax, it's looking like 1.25 inches on the video, but actually you'll have to trust me that it's about 1 inch. Now I added this piece of LDPE that I had laying around here to raise the secondary up to lower the K. And before I had done that, I got these burn marks. I got racing arcs. So in the new coil mount that we built, we're going to want to provide an ability to adjust this thing up and down without having to shove these pieces of plastic in there. But in a pinch, if you wind up with racing arcs, you can just shove plastic. You can put anything non-conductive in there to just get the secondary in a position where it's less influenced by the magnetic field created by this. Okay, so we got about 1 inch here. We know the size of the secondary, we know the top load size, we know the height of the top load above the secondary. The next thing and last thing I'm going to do for javaTC is I need to know what the capacitance is that's coupling to this primary coil. So we have the inductance presented by the secondary, we have the capacitance presented by the top load, by the toroid. That's an LC circuit. The next LC circuit is the primary coil, which provides an L, and then there's another capacitance, and the capacitance is inside this box. And let me see if I can let's get down. All right. Now, like most cooking shows, I've already taken this thing off. Wow, cobwebs. That's how long it's been since this thing has been opened. And we'll get into what we have here in detail in future videos, but I'll just tell you right now what these parts are. This is the trigger mechanism for the transistors. This receives a digital signal and converts it into pulses that run the transistor inverter that creates the pulses that run the secondary. Let's see. This is just a 120 volt transformer that's turning 120 volts down to, I don't know, it looks like 115 volts down to 12 volts AC. I'm using the 12 volts AC to power the digital box here. So this is a driver board that I got online, and I'll explain that in a future video. These are sensors that I made, and they are it's basically sensor transformers that I wound myself, and these transformers do the following thing. They peel off, they measure the pulses that are coming back from the primary, and they send that data into the digital controller, and they allow the digital controller to adjust the frequency of the frequency or the phase. I mean, I guess 1 6 1/2 than the other of the pulses, so that it can stay in tune by itself. So again, this is the power supply that's running this. It's also running a fan. Right here is a transformer that's taking the pulses from the digital box here and converting it to a level and a phase that's appropriate for the driver motors itself. So again, and I'm calling it a motor, but really it's a transistor circuit. Let's see if I can get down here further. So I'm not getting too much. We don't need to know much about this just yet. I'll explain that later. These are the capacitors that create the voltage doubler for that are the power supply for the transistor inverter. But all that we'll get into later. The important thing for javaTC is this capacitor bank right here. And as you can see, I didn't do a very good job of bolting this thing down. I'm going to have to figure out a packaging mechanism for this. But what we've got are 3 strings of 10 series connected snubber capacitors, and these snubber capacitors are Ariovox 2 microfarad. They're Ariovox snubber capacitors, 2 microfarad, 1,000 volts apiece. And I have one laying around here. I'll show you one close up. When you take 10 of them and put them in series, you get 10 2 microfarad 1,000 volt snubber capacitors in series gives you 10 times 1,000 voltage capacity, so 10,000 volts. Each string is capable of withstanding 10,000 volts, and the value of each string, if you do the calculation, turns out to be about 0.3 microfarads. If I put 3 strings of 10 in parallel, I get 0.6 microfarads value. So the capacitance on the primary circuit is 0.6 rather. It's 3 times 0.3. And so it's 0.6 microfarads. And I need to know that when I'm running javaTC. And that'll tell me, that's the C for the primary. The coil, the refrigeration coil provides the L for the primary. And then we have the L and C for the secondary. Okay, I've now measured everything I need to know for javaTC, and we'll go in and check that out. Okay, these are the capacitors I was using for the primary capacitance tank circuit. These things can be found on eBay. I think CTS sells them. They pretty much want about $5 a piece for these. I think you might be able to get them down to $4 or $3.50 a piece. But as you can see, it's an Ariovox RBPS 2.0 microfarad, 1000-volt DC snubber capacitor. They're meant to be bolted on to IGBTs to get rid of transients on the output of the IGBT. We're using them for the tank for the primary. Now, here's the thing about these. As with everything in Tesla coil design, there's some science, and then there's some engineering, and then there's some rumor and innuendo and lore. I've heard from plenty of people that these are not good to use for your tank circuit. I've heard from people that these things inevitably will fail, and they'll fail somewhat catastrophically. They'll burst open, and then you get a problem. I have no reason to doubt the people who tell me that. They're pros. Now, they're pros, and they run their coils for hours during shows that they do professionally. I'm just running my coil in my driveway, and I've never had one of these fail. Now, again, the show that I put on is 15 minutes long, once a month. So these aren't really stressed too badly by what I'm doing. But if you're planning on doing something much more stressful, you may want to use something more hefty than this. And there are plenty of capacitors to be had on eBay. Basically what you want to do is make sure that the voltage that your capacitor string can withstand, you want it to be at least 2 times the maximum voltage you're going to create with your power supply. With my power supply here, I think I might be creating, even in pulses, 1,000 volts or 2,000 volts. And if I put 10 of these in series, then I'm getting 10 times 1,000 voltage withstanding capacity. So I can withstand 10,000 volts, and I'm only creating 1,000 or 2,000 in my circuit. So that's good. And then they're 2 microfarads a piece, and if I put a string of 10, I get a 0.3 microfarad, and that actually balances out pretty well for what I need to have given the geometry of the coils that I'm making. Everything is in balance with everything else. So if you change the value of the capacitors you're using in your tank, you got to change the number of turns in your primary. You got to change the radius of the primary. The coupling changes. The height of your secondary would change. Everything is related to everything else. So there's a balance you must strike, and best thing to do is to strike that balance online with a program, rather than going back and having to rebuild the coil every time, which is what we used to have to do in the old days before there was javaTC. Now we can sit down and run through tens of different coil configurations online and find out if they work before we commit to go build the thing. And that's why we use javaTC. Okay, so enough said about this. Okay, so one of the other things I wanted to show you is this Envirotex. You can get this just about anywhere. I got this at the local hardware store. You can get it at Tap Plastics. You can order it online from Amazon. This is there's a gallon of each. Now what you've got is the actual resin itself and then a hardener, and you mix them 1 for 1. And as you can tell, I've made I think I've coated 2 coils with this, and as you can tell, out of a gallon I may have only used a liter or so. And so you're mixing the hardener with the resin. This is kind of bright. Let's see. Yeah, well, it's hard to see that, but you're mixing the resin with the hardener 1 for 1. So you figure a liter, 2 liters did 2 coils, roughly the size of the the one that I've got there. And what it does is, let's see if we can get in on this. It creates a hard finish. You can see around the edge here. This is probably about a 16th to an 1/8 inch thick, and that's weatherproof. Now, I'm not going to ever run these coils out in the weather, but certainly dust falls off that pretty easily. It is a little bit electrostatically active, so after you've run your coil you can get a shock if you touch this, but that's pretty much true of touching your secondary after you run the coil anyway. But just to show you, and it's easy to put on. If you got to turn it continuously, You put it on actually with a putty knife or a kind of a blade, any kind of a blade, and you spin it continuously. You've got to have the ambient temperature in the 60s to 70 degrees Fahrenheit, and then it'll harden over the course of about 12 hours or so. Hardens enough in about an hour that you don't have to worry about it too much, and then in 12 hours it pretty much is cured enough to work on it, and in a couple days it's completely cured. This again has been on here for years. I've got a couple bubbles in there that really didn't matter very much. You can get the bubbles out with a heat gun while it's still wet. So again, I recommend the EnviroTex.